Hello everyone and welcome back to Explore Engineering. Have you ever wondered how a signal can grow rapidly or fade away smoothly over time? In this video, we are going to explore the fascinating concept of the exponential sequence using MATLAB. Whether you are an engineer, student, preparing for lab experiments, or simply curious about digital signals, this tutorial will make the concept easy to understand. We'll learn what a exponential sequence is, write a simple MATLAB program, visualize the output, and understand its real-world applications. So open the MATLAB, get ready to code, and let's transform theory into an exciting visual experience. Let's begin. So here, exponential sequence, it is a fundamental sequence in the digital signal processing. The definition of the exponential sequence is it is a discrete time sequence of the form x of n is equal to a into r raised to n into u of n, where a is the amplitude, that will be a constant, r is the common ratio, which will be a real number, n here it is a discrete time index, and u of n it is a unit step sequence. Now mathematical expression for this is x of n is equal to a into r raised to n for n greater than or equal to 0, and it will be 0 for n less than 0. Now the types of the exponential sequence based on the value of r are, here you can see the conditions, the type of the sequence, their behavior, and here we'll see one example. So if the magnitude of r it is less than 1, then it is a decaying exponential sequence. That is, it decreases to 0 as n increases. For example, we can take here x of n is equal to 0.5 into n u of n. Here we are considering a is equal to 1. That is, amplitude we are considering it as 1. And here the value of r, it is less than 1. So we have taken here r is equal to 0.5. Next is the magnitude of r is greater than 1. It means that it will be a growing exponential sequence. It increases without the bound. Here we can see we have taken r is equal to 2. Next is if r is equal to 1, then it is a constant sequence. That is, it will be having a constant value that will be equal to the amplitude, that is a, for n greater than or equal to 0. Here you can write it as x of n is equal to a u of n. We are not writing here r raised to n. Instead of that, we'll take it as amplitude because it will be a constant value. Next comes r is equal to minus 1. So here it will be an alternating sequence. That is, it alternates between plus a and the minus a. That is, plus of the amplitude and minus of the amplitude. So we can write x of n as minus 1 raised to n a into u of n, because here we have taken r is equal to minus 1. Here r value is plus 1. Okay, in the third case r is equal to 1, therefore 1 raised to n will be 1. So we are getting here a into u of n. Okay, so we get here a into u of n. That is, for r is equal to 1, constant sequence will be getting the constant value of a, will get a constant value of a for n greater than or equal to 0. Here we have the formula. R we are taking it as 1, therefore any value 1 raised to anything will be 1, therefore we'll get it as a into u of n. So now these are the example plots for these conditions, that is the types of the exponential sequence. If the magnitude of r is less than 1, we get a decaying signal. Here it is decaying. So if magnitude of r is greater than 1, we get a exponential sequence like this. That is the growing. It is exponential only. It is growing exponential. Next, for r greater than minus 1 and less than 0, we get alternating decaying. Okay, like this, alternating decaying. It is decaying like this. Next, for r is equal to 1, we get a constant. See, here we are getting a constant for this value. Okay, constant value a. A is what? Here we have considered a as 1. Therefore, we are getting the amplitude as 1. Now, the applications of the exponential sequence are, it is used in analysis of LTI systems. That is the linear time invariant systems. Solutions of linear constant coefficient difference equations. And it is used in digital filter design and analysis. And it is used in modeling the natural phenomena, that is the decay, growth, etc. So, An exponential sequence has the form x of n is equal to a into r raised to n into u of n, and its behavior, that is the decay, growth, constant, alternating, these all depends upon the values of n. So here in this example, we have taken the value of a as 0.8, that is, it is less than 1. Okay, x of n is equal to a raised to n. What is our main objective here? We want to generate and plot the exponential sequence x of n is equal to a raised to n. For what value of a? For a is equal to 0.8. Okay, so here a is what? A is the common ratio we are taking, n is the discrete time index, and if a is greater than 0 and less than 1, the sequence decays as n increases. Okay? If it is less than 1 and if it is greater than 0, then we'll get a sequence like this, that is, it will decay, okay, as the value of n increases. Now here you have the MATLAB code. This is the MATLAB code for this particular graph. So first is the CLC, which will clear the command window. Then you have clear all, which removes all the variables from the workspace. Then close all, which closes all the open figure windows. Then you have n is equal to minus 10 colon plus 10, which creates the discrete time index from minus 10 to plus 10. Here you can see, you have from minus 10 to plus 10. So this is what we are defining the time index here. Next, you have a is equal to 0.8, which assigns the value of the exponential constant. Then we have x is equal to a raised to n, which will calculate the exponential sequence for every value of n. Here you have a dot operator. Okay, the dot operator, that is dot and raised to sign. Okay, that is a dot operator which will perform the element wise exponentiation. Okay, this will perform the element wise exponentiation. Then you have stem n comma x, which will plot the sequence as a discrete time signal. Here we are getting the discrete values, so it is a discrete time signal by using this stem n comma x. Then you have x label, y label, and the title, which adds labels and title to the graph. Then you have a grid on here. So grid on, it displays the grid lines. You can see here square boxes, these are the grid lines. So grid lines in order to improve the readability. Okay, so here again you can see the code explanation here, and then you have the key observations for this particular MATLAB code. Okay, here we are taking a is equal to 0.8, therefore the sequence decays as the value of n increases, and for negative value of n, a raised to n will be equal to 1 by a raised to n. So the values are at n is equal to 0, you have x of 0 is equal to 0.8 raised to 0, and that will be equal to 1. Okay, so here at n is equal to 1, sorry, at n is equal to 0. Then for n greater than 0, the values decrease towards 0. Yes, no? For n greater than 0, the values are decreasing towards the 0. So here, this is the mathematical equation or mathematical form, and this MATLAB program, it successfully generates and plots the exponential sequence x of n for x of n is equal to 0.8 raised to n for what value of n? For n is equal to minus 10 to plus 10. Okay, this is the program, and this is the output what you get in MATLAB. We will execute this in MATLAB. Okay, so this is the overall summary of the exponential sequence, and here this is another program for the exponential sequence. See, here in this program we are not giving the, we are giving the values for n, that is, we are defining the time index in the program itself. And we are taking a fixed value for a. Every time if you want to generate another sequence with a different value of a, then you have to go and change in the program. So for that reason, this is the another program where you can enter the value of the time index of your choice and the value of a also of your choice. So this is the second program. Okay, you will get the same output, but the value of n1, n2 and a will be of your choice. So here these three commands will be common. These three commands are for the user input. That is, you have to enter the starting value of n, then ending value of n, and the value of a. You have to here this will generate a discrete time index. Okay, n is equal to n1 is to n2. Then it generates an exponential sequence using this x is equal to a dot operation n. Okay, here you can see it computes the exponential sequence. Then here stem x n comma x comma filled. Okay, this will plot the discrete sequence using the stem plot with the filled markers. Fine. Next you have the x label, y label, and the title here, which will add labels and the title to the plot. Next, last is the grid on, which displays the grid for better readability. Okay, and here these are the key observations. Because here we are taking the value of a less than 1, the sequence is decaying. So this is about the exponential sequence with the user input, and this was without user input. Okay, this was without user input because we are giving the value of n and a in the program itself. But here the user will enter the input of his desired choice, then we'll get the output. So this is the second program. You will be getting the same output for that, depending upon the values of n and starting and ending value of n and the value of a. Now we'll execute these programs. Okay. Now you can see the difference between these two programs in order to generate the exponential sequence. So here this is with fixed values of n, and this is where the user gives the input. Okay. So here n is fixed from -10 to +10 only. A is fixed at 0.8 for the first program. There is no user input. Same output will get every time. And this here will get a normal stem plot, whereas here you can enter the value of your choice. Because a is entered by the user, here n is also entered by the user. This is a flexible program, and the title changes with a here. Here a. Now a stem plot with filled markers. Here you have a stem plot with the filled markers. Next, here you can see example for program 2. When you take a is equal to 0.8, you will get a decaying exponential sequence. But when you take a is equal to 2, here you can see it is growing exponential sequence. Okay, and here example 3 is for n is equal to n1 is equal to -8, n2 is equal to 8, and a is equal to 0.5. Again, you will get a faster decaying sequence. Okay. So this is the difference between the two programs in order to generate the exponential sequence. One is without the user input with fixed values. Another one is with user inputs. So now we'll execute the program. We'll see the first program, that is with fixed values here. Okay. I'll copy this program, and you need to start your open your MATLAB. This is the editor window, this is the command window, and this is the current folder into which you are working. So in the editor window, you have to go to the new file and you have to open a script. Okay, here in MATLAB the file is called as a script. So I have opened a script here. Now I'll paste the program. Okay, you can type the program. This MATLAB, it is case sensitive, and carefully you have to type the program. Now run it. Change folder. See, here you are getting the decaying signal. Why we are getting the decaying signal? Because we have taken the value of a as 0.8, which is less than 1, and the time index we have defined from -10 to +10. Now I will change the time index here. I'll make it as 5, and here also I'll make it as +5, and I'll make the value of a as 1.5, which is greater than 1. Okay, now I'll execute. See, here you are getting the growing exponential sequence. But in this program, here I have not changed the value of a is equal to 8. A is equal to 0.8 is there. So I have to change that. That is, I have taken now a value as 1.2. Change it. Now run. See, here you are getting a growing exponential sequence. with a is equal to 1.2. Now we'll see what happens when a is equal to 1. So here I'll change it, a is equal to 1. See, here we are getting a constant amplitude sequence, yes, no, with amplitude a is equal to 1. Fine. Now we'll see the second program. So the second program is with the user input. That is, here the user will give the input of his choice or her choice. Now I'll paste the program here, run it. See, enter the value of n. Enter the value of n. That is the starting value of n. I'll take it as -9. Then press enter. Enter the ending value of n. I'll take it as 7. Okay. Now again press enter. Enter the value of a. I will take it as 0.8. Now enter. Because I have taken the value of 0.8, it is a decaying signal because the value of a is less than 1. And the time index I have defined from -9. See, here it is starting here. At -10, you are not getting any output here. You are not getting any signal here. You are getting from -9. -9 to what? -9 to 7. See, up to here. You can see these dotted dots, no? So, from -9 to +7. Okay, and a is equal to what? A is equal to 0.8. Now we'll change the values again. Once again we'll run it. I'll make it as -5, then press enter to +5, plus enter. Now we'll take the value of a as I'll take it as 2.5. Enter. See, here we are getting a growing signal. Automatically here the value of a is changing, that is a is equal to 2.5. In previous program we need to change the value of a every time here in the in this line, that is the title line. Okay, but because here we are using instruction that is num2 string of a, because of this it gets changed every time here. A is equal to 2.5. Fine. So this is how we get the exponential sequence for different values of a, you can say, or you can take it as r. It depends on you, whatever you choose the variable. So we have seen the program for growing, then decaying, and when it remains constant, what happens when the value of a or r changes. And we have seen the programs without the user input, that is a fixed value, and with the user input. Okay, so you have successfully learned how to generate and visualize an exponential sequence using MATLAB. We have understood the program, observed the output, and discovered why exponential sequences are important in digital signal processing, communication systems, and control engineering. So keep practicing by changing the values of the sequence to see how the graph responds. Learning becomes easier when you experiment with code yourself. If you found this video helpful, please don't forget to like, share, and subscribe for more MATLAB and DSP tutorials. Thanks for watching, and I'll see you in the next exciting learning video. Happy coding!